Welcome, fellow chemists, to the second video in my stoichiometry series. This one covers limiting and excess reagents. I'm going to lead you through three different methods of finding them. The first uses stoichiometry exactly as demonstrated in the first video, and the second requires a slight twist. The third and final one involves a clever use of ratios. But before I dive into those methods, you actually have an idea of limiting and excess reagents in a different context. Take this recipe for Thompson's plum pudding. On second thought, how about my personal favorite for chocolate chip cookies? One day I decided to make my own and check the pantry for these ingredients. I found I had exactly what I needed for most of them except for the eggs and chocolate chips. How could those amounts be described? There are fewer eggs available than the recipe calls for and more chocolate chips than needed. Having more of any ingredient than required means it is in excess, and having less of any ingredient means it is limiting. I'm sure in the context of cooking and baking, you can identify limiting and excess ingredients quite easily. It's the same idea when it's about a chemical reaction. On the screen now is a typical limiting excess reagent question. The first thing to notice compared to what we encountered in the previous video is there are two values given in the question. However, before we look further into that, this equation is not balanced and we do not have the molar masses determined for any substances yet. I know you watched my previous videos on how to find these values, so I'll just give them to you as a token of my appreciation. So now we can focus on the question which specifies limiting and excess reagents. I've referenced these in relation to baking cookies, but now let me connect it to chemistry. The limiting reagent is the substance that is fully consumed in the reaction. Since the reaction will stop once this reactant runs out, it limits product formation. The excess reagent is not fully consumed, and therefore some is left over when the reaction is finished. This question wants us to identify whether methane or oxygen gas is the limiting reagent, and then determine how much excess reactant remains when the reaction is finished. To answer this, let's head over to the MethodOne Clinic. The beauty of what we are about to do is that it involves using stoichiometry exactly as it was in the first video. This question gives us two substances but does not specify which substance we want to find. Without a specific substance, we must make an arbitrary choice, so let's go with water. Next is a stoichiometry calculation, and since it is first in the question, let's start with 1600 grams of methane and determine how much water would form if all of it reacted. This requires setting up the grid using the style from the previous video. The result of the calculation is 3,600 grams of water. Now we will do that again, but we must replace methane's given mass, molar mass, and coefficient from the equation with that of oxygen. The calculation is easy enough and comes out to 3,375 grams of water. With the stoichiometry done, we must now interpret what the two answers mean. According to the calculations, 1,600 grams of methane is capable of producing 3,600 grams of water, and 6,000 grams of oxygen only makes 3,375 grams. According to the earlier description, oxygen must be the limiting reagent because it produces less water, which means methane is in excess. We did good work, but this only answers one of the questions as the other concerns how much excess reactant there is. In order to do that, we can use the 3,375 grams produced as a given and work backwards to find out how much methane must react. Water's molar mass goes in the bottom left with its coefficient from the equation in the bottom middle. Above that goes methane's coefficient, then its formula mass next to it completes the grid. When we perform the calculation, the result is how much methane actually reacts, and it's 1,500 grams. If we were originally given 1,600 grams of methane and only 1,500 grams reacts, then there must be an excess of 100 grams. And now let me summarize all of those steps. First, use stoichiometry to determine how much of a product is formed from each reactant given. I'm going to add the subscripts to the letter Z as a reminder of which reactant was used. Second, identify the limiting reactant by choosing the one responsible for making less product. Third, in another stoichiometry calculation, use that smaller amount produced to find out how much of the other reagent is actually used. Finally, determine the amount of excess reagent by finding the difference between how much was originally given and how much is actually used. The second method requires the same stoichiometry, with the difference being we will directly compare the two reactants to each other. Only because it's first in the question, we'll start with 1,600 grams of methane and determine how much oxygen gas reacts with it. So we'll put all methane's information into the grid, followed by oxygen's coefficient and molar mass. We calculate an answer of 6,400 grams of oxygen. Now you may know what this means already, but we could have easily started with oxygen and determined how much methane is required instead. Had we done so, we would have found that 1500 grams of methane reacts. As in method 1, we once again compare the two results, but this time we take what was given for each reactant and subtract how much is actually needed. We find that we have 100 grams more methane than required, but are short 400 grams of oxygen. That 100 grams of additional methane should sound familiar because it is exactly the amount of excess we determined in method 1. The oxygen is limiting because there is 400 grams less than the amount required. Method 2 saved us one stoichiometry grid, but method 3 doesn't require them at all. And that's because we use the available information differently. According to the equation, 1 mole of methane reacts with 2 moles of oxygen. The question gives us masses of reactants, so we need to ensure the units match. We could convert to moles, but since we've done everything else in mass, 1 mole of methane is 16 grams and 2 moles of oxygen is 64 grams. We compare those with what the equation gives us, 1600 grams of methane and 6000 grams of oxygen. The given methane is 100 times the required amount according to the equation, while oxygen is only 93.75 times. Therefore, we can conclude for the third time that oxygen is the limiting reagent and methane the excess. While the logic is relatively straightforward, you may be wondering how we can turn this information into the amount of excess. We could use stoichiometry grids, but I'm avoiding those. If we have 100 times the methane and 93.75 times the oxygen, that means there's an excess of methane 6.25 times what the equation says. Since the equation requires 1 mole, or more appropriately 16 grams of methane, multiplying the two together reveals the excess amount to be 100 grams. Now that you've seen 3 methods for how to approach these problems, pause the video and try to answer this final question. I'm going to use method 3 because of its coding simplicity, but you should get the same result even if you use a different one. This time we're given much smaller masses of methane and oxygen, but since the equation is the same as before, the given moles of methane and oxygen haven't changed, and therefore the required masses in the equation are the same too. The 11 grams of methane provided is only 0.6875 times what the equation requires, while there's a slightly greater amount of oxygen at 0.75 times. This makes it easy to identify methane as a limiting reagent and oxygen as excess, but how much excess is there? Taking the difference between those two amounts, there is a tiny excess of 0.0625 times what the equation says. Multiply this by the mass of oxygen from the equation, and we find an excess of oxygen to be 4 grams. Now I'm not completely ridiculous. If you did method 1, here is all you're working out. And if you did method 2, here is that as well. At the end of the MethodOne clinic, I summarized all of the working out because if you're watching this video, you are probably new to stoichiometry and that method was the most straightforward. I know you may feel I am a monster for not summarizing 2 and 3, but, well, this video is long enough without them, and like Buster Bluth, you'll be alright. Since I know you are scholarly and enjoy scholarly pursuits, I'll see you again when I cover % yield, but until then, thank you very much for watching.